These are the notes for the first day of section 3.2 on what's called implicit differentiation. So I'm going to have the 2 days be, today's notes are just going to be sort of an introduction, visually seeing what's going on, and then we'll do a little bit more of the actual powering it out tomorrow. So implicit differentiation, and these notes are not in your note packet. You should be taking them on a blank sheet of paper, and they're going to be ed puzzle for test points. Whenever I ed puzzle, I go test points on it. It means it's a really important section. Implicit differentiation. So the first thing I think that we need to discuss is, what does this word mean, right? So we have two kinds of functions. Functions that we call explicitly defined, which is what you're used to most of the time. You've had some implicitly defined functions in your math past. You just didn't know that's what they were called. So implicit functions. So explicit functions are y explicitly as a function of x, like your linear function, your quadratic function, even the square root of the quadratic function. You can take its derivative using the derivative rules. So if I were to do dy dx on this one, I would raise it to the 1/2 power. I'd bring the 1/2 out front, leave the 4x squared plus 1 intact, drop the degree, then times the derivative of the guts. And I just straight up take my derivative with respect to x is what I call it. Or maybe y is a function within a function, but it's still simply a function of x. And maybe it didn't even say y. Maybe it said, sorry, I'm trying to engage my eraser here. Maybe it said f of x equals sine of 2x. And when we take its derivative with respect to x, when we do the derivative of y with respect to x, we say that it's cosine, leave the guts intact, times the derivative of the guts, which is 2. All right. Now, another one would be y equals, let's say, the square root of 25 minus x squared. Again, that is explicitly y as a function of x. Now let's go over and talk about what the implicit functions look like. Implicit functions would maybe look like y equals the square root of 4xy squared plus 1. Notice I'm mixing the x's with the y's. Y isn't explicitly a function of x. It's an expression or a relationship between x and y. This needs a special process called implicit differentiation. Same here. Perhaps we'd have our y equaling the sine of 2xy plus 1. Again, it's not explicitly a function of x. And lastly, what if it was x squared plus y squared equals 25? Again, not explicitly a function of x. It's a relationship, or a relation it's called, between x and y. So that's the difference between implicit. For implicit, they're written as a function of x only. For implicit, you'll see the x's mixed with the y's on the same or even both sides of the equation. So the one I'm going to focus on right now is this, okay? Maybe you recognize this as the equation for a circle from Algebra 2. So let's go take the implicitly defined relationship. This is a circle centered at the origin with a radius of 5. Whoop, not the best. I'm going to share my Desmo screen for a second and go graph that. Actually, I'll graph it when we're done, but pretend that doesn't look so much like a potato. Now let's go to a point on this circle. And again, anything on it, the x squareds plus the y squareds have to equal 25, like 0, 5, 5, 0, but I don't want to use those because those have vertical horizontal tangent lines or derivatives that don't exist, and horizontal tangent lines are derivatives of 0, so that doesn't prove my point. I'm going to use the point 3, 4, which I know is on that circle because 3 squared plus 4 squared equals 25, right? So there's the point on the circle. Although this isn't a function, keep in mind it doesn't pass the vertical line test, a derivative still exists there. There is a slope to the tangent line. And honestly, most functions that occur naturally, or relationships between quantities that occur naturally in the real world, are not functions. So that's kind of interesting, but they still have rates of change and instantaneous rates of change and still a lot of calculus. It's just we have to approach it differently. But I'm going to say for this implicitly defined function, I actually could solve it for y and get it explicit. I would say y squared is equal to 25 minus x squared. Equivalently, y is equal to the square root of 25 minus x squared. So both of these right here, watching yellow, are actually the same thing, except this one's a function. It's actually a semicircle. You might say, LaRue, you should have put a plus or minus in front of it. I actually should, but I really am only concerning myself with the top half of the circle, not the bottom half, because that's where my point of tangency is. But if I piece together the two functions, the positive square root of 25 minus x squared and the negative, my TI-84 can graph that. I just would have to do y1 equals the positive, y2 equals the negative, and it would graph two different semicircles. Whereas if I go to Desmos, which doesn't require the relationship to be a function, I can enter x squared plus y squared equals 25 and it'll make the circle. So let's take the derivative, which you already know how to do when it's explicitly a function of x. We rewrite it so that we can see the power. We launch into the chain rule. We bring the 1/2 out front. We knock the power down 1, disguised as denominator over denominator. We multiply by the derivative of the guts. And then we clean it up. 2's gone, negative x on top, square root of 25 minus x squared on the bottom. That is the derivative of y as a function of x. Notice all I need to do to find the slope of the tangent line right here is plug in a 3. So the derivative of y with respect to x at x equals 3, because it's only a function of x. I took this implicitly defined function and I solved it for y. And you might say, well, that's what I always want to do. Oftentimes it's difficult and not even possible to solve a relationship for y. So I just put an easy circle up here, but a lot of times, and most of the time, when we have these implicitly defined functions with the x's and the y's mixed, we're not going to be able to solve it for y. So again, when I go plug my x in of 3, I'd get a negative 3 over. I'd have 25 minus 9 because I'd be squaring that negative 3, square root of 16 or 4. What it means is the slope of the tangent line at 3, 4 is negative 3/4. All right, now I'm going to go to the next page here. Before we do that another way, I want to discuss how what if we change the variables? All right. So I'm going to go over here and tell you the derivative of x cubed with respect to x. Maybe I had said y equals x cubed. Maybe we had said g as a f of x equals x cubed. The derivative is just the power rule. I bring it out front. I knock it down 1. I bring it out front, and the reds are my derivatives. I knock it out front. I bring it out front, I knock it down 1. I bring it out front, I knock it down 1. But really, see this variable match? It means that the derivative of the guts is 1. So really there is a chain rule going on. I'm doing 3 times x squared times dx dx, which is 1. 3 times x squared times dx dx, which is 1. So when there's a variable match like that, it's exactly how we've been doing it, because we've always had these explicitly defined functions of x. So you'll notice I've always said with respect to x. But what if it was the derivative of y cubed with respect to x? There's not a variable match there. And so when I take the derivative, I get 3y squared times the derivative of the guts, which is dy dx, and that is not 1. So you really have to watch the variables. So next thing up, what if y equaled sine of 2y, not 2x, so it's not y as a function of x. When I do my derivative, I will get cosine, leave the guts intact, times the derivative with respect to x of 2y. You might say that's 2. Nope. If it was an x there, it's 2 times dx dx. But when there's a y there, it's 2 times dy dx. It's a little confusing, and that's why I'm doing an intro to the implicit rule of differentiation. So next up, what I want you to do is write, let's say w is equal to t cubed plus 4. We would say w is a function of t. So if I said dw dt, which is really the derivative of t cubed plus 4 with respect to t, there's a variable match. So that's exactly what I would think it would be. It's the derivative of t cubed, which is 3t squared, technically times dt dt, but that's 1, plus the derivative of 4, and constants are always 0. That was easy because of the variable match. Okay, we have to be very careful with that. Now, let's go back to our circle. All right, now, I sound very, sorry, I didn't mean to say it like that. So we just did, I'm going to go back a page. We had our circle centered at the origin with a radius of 5. It was given to us implicitly as a relation between x and y. That's not a function. A circle violates or does not pass the vertical line test. But I was able to solve it for y as a function of x and take its derivative with the chain rule. But what if I wanted to use this new process called implicit differentiation? We use it when we see those x's and y's kind of mixed on both sides of the equation, and we can't solve it for y easily, if at all. All right, here's how it starts. You still take the derivative. You're going to take the derivative of both sides of the equation with respect to x. You're still going to use all the rules we've been using. We know that sums can be broken apart. So this is really, and I'm going to show every step, this is really the derivative of x squared with respect to x. Keep in mind, if it was a product, I'd need the product rule, plus the derivative of y squared with respect to x equals, and the derivative of any constant is 0. Remember y. If y equals 25, then if this is the x-axis and this is the y-axis, y equals 25 is a horizontal line up at 25. And the slope of the tangent line anywhere on a horizontal line is 0. So the constants with respect to any variable are always 0. Now this is where things are different. Variable match. The derivative of x squared with respect to x is 2x. It's actually 2x dx dx plus no variable match. So this will be 2y times the derivative of the guts, and the guts is y. So it's 2y times dy dx, still equals 0. Keep in mind, I'm trying to find the derivative here. I'm trying to find dy dx. That's my ultimate goal. You might say you already found it. I did. I found it explicitly, and now I'm finding it implicitly. So when I solve this for the derivative, I'd subtract the 2x off, divide by the 2y, cancel, and I get negative x over y. You'll now notice that my derivative is not a function of x. It's got both x and y in it. So remember that circle, that dy dx, at x equals 3? Explicitly, we got that as negative 3/4. Now we're doing it at the point 3, 4. And this says you do negative the x over the y. You'll notice I have the same answer, I just needed the x and the y. We did it right over here as a function of x. I just plugged x into this explicit equation for x. I took the exact same relationship, didn't solve it for y, and I used this process right here that's called implicit differentiation, and I arrived at the same derivative. So let's go through one. This right here, I have no clue what the graph of it looks like. We'll go graph it when we're done on Desmos. But I can see that it certainly isn't y as a function of x. The x's and the y's are mixed on that left-hand side. And if I were to tell you to solve that for y, you would be on the struggle bus, if it's even possible. So here's our steps. Our implicit differentiation steps are, number 1, we're going to take the derivative of both sides with respect to x. So I'm going to go over here and take the derivative with respect to x of y cubed plus y squared minus 5y minus x squared. And that'll be the derivative with respect to x of 4. Step 2, if no variable match. What do I mean by that? The derivative of y squared with respect to x, the derivative of y squared with respect to x, the derivative of y with respect to x. Those three in green have no variable match, but the derivative of x squared with respect to x does. So if no variable match, then make sure you're thinking of that chain rule. You never thought of the chain rule when I said, what's the derivative of 4x cubed plus 6x? You just said it's 12x squared plus 6. It is, because the guts is x and dx dx is 1. I've said that a lot, but just to make sure that's kind of hitting home there, right? So let's go back up here, then use the chain rule. So here's what I mean by that. I'll bring the 3 out front, I'll knock it down, but now the guts is dy dx. And most kids will choose to write y prime when they use implicit instead of dy dx, just because it's cumbersome. I'm fine with that for these straight up implicit ones. Once we go to the word problems though, you are going to want to write 3y squared times dy dx. And it won't actually be a function of x, it'll be a function of time. It'll be stuff changing as time goes by. Just to give you a little preview of that. For example, perhaps there's an oil spill and it's increasing and spreading as time goes by. And there's lots of things changing at the same time. The radius of the oil spill is growing, the area of the oil spill is growing, all that, or the surface area, I guess. And we might say, well, you know what? I want to know how the area is changing over time. Like, I want to know if the area equals pi r squared, how is the area changing as time goes by? Well, maybe we only know how the area is changing as the radius is changing, but we know how the radius changes as time goes by. Now, if that doesn't make sense, that's totally fine. But I'm just telling you, we need to see this sort of dx, dy, dx notation eventually for the word problems. But for ease of computation, I'm fine with you not writing dy, dx here, but make sure you understand that's what it is. Go ahead and write y prime. So we've got the 3y squared times the derivative of the guts, which is y prime, plus, now we're onto this one, no variable match, so plus 2y times the derivative of the guts. Next one is minus 5, right? And the derivative of the, if it was minus 5x, we'd say minus 5. But it's minus 5 times dy dx. It's the derivative with respect to x of a negative 5y. We bring the constant out front, and we don't just have negative 5 dx dx. We have negative 5 dy dx. On the next one, we have a minus x squared, and that is with respect to x. So that's just minus 2x, because dx dx is 1. And on the right, we have a 0. So step 2. Step 3. What would it be? Let's consolidate or collect. Let's call it that. Collect all y prime terms on the left. Okay, so let's go up there. We want to keep this guy on the left. 3y squared y prime. That's got a y prime in it. We want this guy to stay on the left. So plus 2y y prime minus 5y prime, but the 2x is going to move over. Then what we do is factor it out, because remember our goal is to still find dy dx. So don't lose track of that. We're still taking a derivative. I want to know what's y prime. Factor out y prime and divide. So over here on the left, I'll factor out the y prime. I'll take it out of here, leaving a 3y squared. And then I'll take it out of the next term, leaving a 2y. I'll factor it out of the third term, leaving a minus 5 is equal to 2x. So now to isolate, oops, sorry, that should have been a prime right there. To isolate the y prime, I would just divide both sides by 3y squared plus 2y minus 5. Now, you'll notice my derivative, which is dy dx, I just allowed you to use that shorter notation of y prime, is a function of both x and y. All right, one more, and that's it for today. All right, you'll practice these level 1, these are called on Delta Math, and then we'll dig into more about what this means, what it looks like tomorrow. So, example 2. If you see this, anytime from here on out, something that looks like this, you're like, oh, this is implicit, because it's not y equals 8x plus 4 or 8x cubed minus 6x. They're mixed together on that left-hand side. Could I solve it for y? I don't know, but I'm not even going to bother because it looks like it'd be messy and I probably can't even do it. So I'm going to take the derivative with respect to x of all of it. Whoops. Y cubed. The derivative of any constant is just 0. For any terms that don't have a variable match, which would be these 2 in green, I've got a y in there when I'm doing it with respect to x, and again a y in there. So the green ones require our new process. The derivative of x cubed with respect to x is still 3x squared. Be very careful. Stupid eraser. All right, there we go. So be very careful. So this is just like our first day of the power rule, right? But you remember how I used to always say with respect to x, and you're probably like, why is she saying that? Right? So the next one, this is a product of 2 functions, okay? And remember, y is a function of x. X is just x. So when we do this, we have to think of the product rule. So we would have first d second, which would be dy dx, which would be y prime, plus second d first. And the derivative of 6x with respect to x is just 6. One of the biggest mistakes people make with this right here is just going the derivative of the first one, 6, and then they go to times the derivative of the second one, y prime. You need the product rule. It'll kill you if you miss it. Product rule, okay? I'm going to repeat it because it's the last one we're doing. I did the first function, which was this linear function right here, times the derivative of the second function, which is just y to the first. So it's just dy dx, which I said go ahead and write it as y prime, plus second, which is the y, times d first, which would be the 6, plus the derivative of y cubed. You might say, oh, that's 3y squared. It is if it was dy cubed dy, then it's 3y squared times dy dy. But this is 3y squared times dy dx, which we can call y prime. What's step 3? We collect all y prime terms over on the left-hand side because that I'm trying to solve for y prime. So I'll keep that 6xy prime there. I'll keep the 3y squared y prime here. But on the other side, I'm going to subtract off the 3x squared and the 6y. Next, I factor the y prime out of the terms on the left. I leave the right intact. Lastly, I divide both sides by what's in the way. So I'd have a negative 3x squared minus 6y over 6x plus 3y squared. Factoring is always our friend. So let's factor a negative 3 out of the top. Let's factor a 3 out of the bottom. Cancel, and we can go ahead and leave it. This is our dy dx. Notice to find out what the derivative is at any specific point on the graph of this relationship. I'm not saying function because I don't know if it's a function. I would need to input both the x and the y because it's not explicitly a function of the x coordinate. So last step before I leave you, all right, your assignment is delta math. Just it's level 1, so it shouldn't cause you too many issues, and I didn't assign very many. We'll get into the more deeper meaning of this stuff tomorrow, but I do want to go graph this one for you. So I'm going to share my desktop here, and I think I have Desmos open on it. Whoops, did I go to? I think I shared my iPad again, so I want to share my desktop. Hopefully it's showing. If not, big deal. All right, so I'm going to go graph that original relationship. It was x cubed. Notice I couldn't do this on my TI because when you buy them, they say they're functions graphers, and my bet is that this is not a function. Maybe, but we'll see. 6xy plus, I think I have caps lock on. Sorry, I'm going to take my cap lock off. So there's my cubic function of x, right? But then it went implicit because I had the x mixed with the y, and then it was plus y cubed, and then it was equal to 8. X cubed plus 6xy plus y cubed equals 8. Why is it telling me it's a line? That's interesting, isn't it? That's really weird. I wonder if I have a setting off here. I just can't imagine that that thing's a line. Well, interesting. Anyway, that wasn't a good one to try to prove my point. I'll probably take it off the video. Have a good one. We are done.